Should we wait another minute and start? Okay, so welcome back to the second Landau lecture by Yair Minsky from Yale, who will tell us about stable norms, laminations, and horocycle dynamics.
Thank you. Thank you for coming back. I appreciate that. Okay, so let me say what I'm going to do. So we have two lectures left, right? So there's today and Tuesday, and I should say I didn't. The first lecture I didn't say everything that I had been thinking I would say, but I think I said everything that's useful for the second two lectures. So I think I can just kind of continue from there. Today I want to do geometry. In particular, I want to talk about stable norms and Lipschitz maps. So this is kind of not that new a topic. It shows up in various parts of mathematics, but we came to it, I'll say we are, through these applications to dynamics. So the dynamics part will be on Tuesday, and it will be about horocycle flows in certain kind of hyperbolic measures. So if you're not sure why I'm bothering with the things I'll talk about today, then the answer will be on Tuesday. Why? Okay. All right. And this is work with joint work with James Farr and all. Okay. And as last time, I'll feel free to ask questions. I need to write questions. Okay. So I want to start with an actual sort of general definition. It's kind of between topology and geometry. So I think this definition, I don't know the literature super well, but I think it's due to Federer and is kind of relevant in geometric measure theory. It's called the stable norm on homology. So if M is a manifold, the stable norm on this, say the kth homology of M, our coefficients, is the following. I want to take, so if I take a homology class, alpha, then its norm will be basically the smallest representative, the size of the smallest representatives. Did I say that M is Riemannian? I did not. So what is this? It's just the infimum of overall expressions like this. If you write down alpha as the homology class of a chain, A-I-C-I, this is just a k-dimensional chain, and these things are simplices, and these are the coefficients. So you look all such expressions, and then you just write down the size of this in the manifold, which is to say the sum of AI absolute value times the volume, the k-dimensional volume of the simplices. So just do that. It's not hard to see that this is in fact a norm. And I'm very quickly going to reduce to think about the case where k is equal to 1. And if k equals 1, then we're talking about length. Right? Volume is just length. And so we're just looking for the shortest representative of a homology class. It's pretty clear that the shortest representative should be a geodesic object. But not to mention, there's another way to think about the same thing, which is this. You can think of this as follows. I want kind of a geometric picture to put into this. So suppose that I had M. I could look at, let's call it M tilde to be the universal abelian cover of M. So this is the cover whose deck group is the homology group, the integer homology group. So this on this thing we have, in other words, M can be written as M tilde modulo the action of H1 of M. Z. And then we can define another thing which turns out to be equivalent, which is the following. You just take, let me draw kind of a cartoon of this thing. So suppose there's some kind of, I'm drawing some kind of picture that's supposed to make you think of some Riemannian manifold with a Z2 symmetry. Okay, so like it's not actually planar, it's some Z2 cover, say, of M, something like that. And then I want to kind of think about distances in this manifold. So if you take any, if you take an integer element here and you look at a point and its image under that integer element, then you can measure the distance between these 2 points. And if you move the point to the base point a little bit, it only changes the distance by a bounded amount. And so you could take a kind of limit. So you could say the following thing. So if you take maybe x, maybe alpha, in h1 of mr, then you could take the following thing. You could look at large multiples of alpha, take very large r, and then let me use this notation to mean the integer part. So this is some element in real homology, but you can approximate it by something here. Now it acts as a deck element on M tilde, and now you can take this, now you can take, say, a base point, let's call this base point O, take a base point in the manifold, and you can act on that base point by this element of the group, and compute this distance in the cover, that's what I just drew here, and then take then divide by R, and take a limit. I just realized that it's appropriate to write from right to left in this country, right? So this is some kind of a limit, and it's an exercise that this is actually the same thing. This is the same thing. So this norm is kind of measuring. I want to say it's not obvious because this is the length of some path which represents this homology class, whereas these could be sums of different loops, not a single loop, right? So there's a difference between what's going on here and what's going on here, but in the limit they end up being the same. Not super hard to see. And so this is another way to think about this. And now it's giving us some kind of description of the geometry, the large-scale geometry of this cover of the surface. And of course, if you're only interested in very rough description of the large-scale geometry, then you could just say, well, the large-scale geometry of this universal cover up to, if M, say, was compact, it should just look like z to the k, z to the whatever the dimension is of the homology. But there's something finer going on if you're actually interested in whatever the Riemannian metric here looks like. So, okay, any questions about these definitions? Okay, and my goal today is to kind of lay out what the things we're interested in knowing about this picture, and do a couple of extended examples that give a little intuition into what kind of behavior we see. Okay?
This means claiming this equality that it doesn't matter which representative of alpha you take, still have.
Oh, so this is, here alpha is not a representative. Alpha is a homology class. And then this is still a homology class, and then this is just, okay, fair point. What does it mean to take the integer approximation?
What does it mean that you take alpha acting on 0? Oh, I see. Think of it as.
Oh, I think it is an element of this group acting on the manifold. Right, so the homology group acts on this cover. Yeah. Okay. Okay. Okay, so in the title, in the description I said there would be stable norms in Lipschitz, I didn't say what, Lipschitz maps I should have written. So I want to look at this a little bit more carefully. So maybe I'll say it actually this way. First of all, let's say it over here. So somehow optimal representatives for homology classes should somehow be geodesics. So, either geodesic chains, or here you see a kind of geodesic that at least asymptotically is going to be a good representative of the homology class. Okay, but we could also look at the, I guess maybe I'll just start with the kind of abstract picture. So if you look at if you look at this norm on this vector space, and what does a norm look like? It has a unit ball, right? So let B1 be all the elements with norm less than or equal to 1. So there's some picture, well, we don't know, right? Some convex symmetric ball in the plane is the unit ball. And if you want to understand what this norm looks like, that means you want to understand what this unit ball looks like. And one of the things you should always do when you think about this picture, since it's a convex set, you should look at supporting hyperplanes and understand what they look like. So somehow you should be thinking of this picture, right? So any point on the boundary of the ball should be, through it should pass a hyperplane like this. And a hyperplane, and maybe, depending if it was you might have a flat face somewhere where the hyperplane passes through the entire face, or it might not. So there's kind of an interesting story happening in the dual space. The hyperplanes are determined by elements of cohomology. So here I can think of this hyperplane as corresponding to some element. So maybe if this is the point x in the boundary, there's some element in the dual space. Maybe we'll call it gamma in the dual space, which is just a cohomology. And what property does it have? It has the property that gamma of x is exactly the norm of x, which is 1, and gamma of y is less than or equal to 1 for all y in the ball. And so that is what makes it a supporting hyperplane. And because it's an element of cohomology, it gives me a little bit more of a geometric thing, namely gamma is represented by a 1 form in the manifold. So gamma is represented by many, not one, but many 1 forms. Say omega on M. Okay? And you can integrate omega to get a function on the cover. Okay, so you can define, we will call it f omega from m tilde to r. How do you define this? Well, you say you pick it. We still have a base point somewhere, so you let f omega of some point z in here. It's called p. It's just the integral from some base point to p of this form omega. What properties does this map have? So f omega so maybe I don't want to. What do I actually want to say? Well, so f omega has an equivariance property, f omega of, say, x, well, let's call it p. What do we call elements of the group? We didn't have names. Suppose that alpha is an element of the group again. Then if you look at alpha acting on some point p, that's the same as this, right? Where the 1 form is gamma, right? The classical gamma. Right? So gamma, the equivariance of this map is controlled by gamma. So gamma could. Okay, there's nothing particularly new in this story, but I want to point out that we have this map that somehow is supposed to see the fact that x has norm 1, but it's not yet clear how it sees it. So where's the point of that? So right. So f is the map that I want to ask whether it's a Lipschitz map or not. So the Lipschitz constant of f is the same as the L infinity norm of the 1 form that gave rise to it. Right? In other words, the 1 form is just a derivative of the map f, and so if the derivative has some bound, then that's the Lipschitz bound of f. And I want to point out there are 2 numbers now that one can think about. One is what's the Lipschitz constant that I get here, and the other one is the norm of omega. right? So, yeah, so I guess the question is this. So is this Lipschitz constant, well, can we find omega representing can we find omega representing our one form gamma such that the L infinity norm of omega is equal to the stable norm of gamma. Okay, that's the. So I want to say that one direction is always going to be true, so that which way is this? Yeah, the stable norm is always less than or equal to the Lipschitz constant of this map. You can sort of see that from this thing. You can't. Yeah, if you take any homology class, since you can represent it by a short, by something of length equal to its stable norm. Am I saying this right? I wrote this the wrong. This is the co-stable norm. Sorry.
Oh, okay.
Sorry. Let me write. Yeah, I've got too many things on the board. This is sort of a shame. So let's define the co-norm of gamma. Gamma is a dual element, right? It's the suit over all alpha non-zero, say, of the norm of the stable norm of alpha. Sorry, of the size of gamma of alpha, which is a number divided by the stable norm. Right? That's the usual definition of conorm, and that's what I'm saying here. So I'm saying that ratio cannot grow any cannot be any larger than Lipschitz constant of F, because F controls how much you stretch things. But equality is not so obvious, and it is in fact a theorem that you can. So I think in this, so I'm not sure who to attribute this theorem to, but it certainly follows from a relatively recent theorem of Yair Minsky, but it really, I think, has an older, in this setting, it has an older history, which I should not, which I don't think I can quite describe. But it goes back, I think, to the beginnings of the subject. Anyway, it says that the answer is yes. In fact, so there exists an omega and an F omega such that M, now M, what did I assume about M to make this work? Maybe I should be more careful. Let's now assume that M is hyperbolic, so that I can be sure this is exactly right. Hyperbolic, but of any dimension, actually. So if M is hyperbolic, then the answer is that you can actually realize this norm as the Lipschitz constant of a map. So this is kind of the best map, or a best map you could have for this purpose. So there is a one form and a corresponding map such that M admits a geodesic lamination. And so now we're back to what we talked about 2 days ago, 3 days ago. Where the size of the one form, well, let's just even say an oriented geodesic lamination, such that omega is equal to 1. In this case, the norm is 1. So actually, let me be clear, this is the norm along lambda. So that so the picture looks something like this. Somehow M is some compact manifold, and there is a lamination of the type I talked about last time, so it's kind of some kind of closed union of disjoint geodesics in the metric, so that, well, the picture is oriented, and along the leaves the map is stretching, the map f omega is stretching exactly by factor 1, and it's less than or equal to 1 everywhere else. Okay?
So this is the minimum of the Lifshitz behavior?
Yeah, this is like the kind of smallest possible Lifshitz constant. In our paper, we call this such a map tight, which just reminds us, the word reminds us that there's some kind of a locus where you're forced to stretch by the maximum amount. And so it's tight along there. Everywhere else it can relax a little bit. And I will say that, so another connection to the story is what are known as Thurston stretch maps, which have a similar story, except that the maps are not from this manifold to the realignment of the circle, but rather to another hyperbolic manifold. So all of this stuff works not just for functions the way I'm talking here, but actually to the setting of maps between manifolds of any dimension.
It's also a notion of Thurston norm, so it's similar.
Thurston norm is a norm on second homology, which
Second.
on second homology,
But
but it's not quite the same. It has a similar flavor. The difference is that Thurston norm measures the topological complexity of a representative, and this measures geometric size. So they are.
So it's
not
not
the same.
it's purely on the level of chain complexes, the Thurston norm.
This is without the
Yeah.
volume, right? It's
No
the same
volume.
form.
Right, the Thurston norm doesn't use the volume, and this form measures volume, or in this case length. So in fact the norms are quite different in character. We can, go through
Is
an
this,
example.
here you use L1 norm, make a difference if you use other...
I think you do. I think you can, and you do. I think it does make a difference. I don't know what to say about other settings, but yes.
There's a Gromov norm which does measure volume, and it is equivalent to the first one.
For hyperbolic, the Thurston norm on the top homology of a hyperbolic manifold. The Gromov norm in the top homology of a hyperbolic manifold is equal to.
Find Gromov norm in any same formula.
But if you measure the volume of a surface in a higher dimensional manifold, its volume and its Euler characteristic are not the same. You can have smaller or bigger.
Still,
Right? So in the same manifold, you could, they're related if the manifold is compact, but they're not exactly the same.
yeah, that's
Um,
true.
So
It's only in dimension 1, this theorem?
this,
Physics?
no. So let's see. So yeah, the theorem. Okay, the theorem as I'm using it is about functions. So the target is one-dimensional, and then you maybe shouldn't be surprised that the stretch locus is one-dimensional. But there's an interesting fact that if you look at maps from a hyperbolic manifold to a hyperbolic manifold of any dimensions, the stretch locus is still a one-dimensional lamination.
And is there a connection between the homology class and the lamination?
What, say again? Oh, sure. Let's see. There's a sort of subtle connection. So the lamination will support some measures, and these measures. So in the picture I drew up there, there's sort of a picture like this. There might be some associated to omega. There might be a facet, and then the measures supported on the lamination will give you homology classes that live on this facet. So the lamination we supported more than one measure. For example, it doesn't have to be connected, but also it doesn't have to be ergodic, uniquely ergodic. So it might have several invariant measures, a simplex of invariant measures, and they could lie in some facet of this ball. In general. Yeah.
Could you explain what you mean by omega equals 1 around lambda?
Yeah, sorry. I mean that if you take a positively oriented unit tangent vector, then the value of omega on that unit tangent vector is 1. This is a little telegraphic. So, right, so the form gives you, right, so the form gives you a value on every tangent vector, and of course there's a kernel where it's 0, but somewhere, but in the direction of the lamination, the statement is that it's exactly 1. So if you integrate along the lamination, the difference in the function, the integral of omega, will be exactly equal to the length. So another way to say that is that in the cover M tilde, let's actually do that. In the cover of this, which is M tilde, there's some kind of bigger manifold, and now this lamination lifts to the cover in some way. And then there's a map, here there's the map to R. Right, that's actually where the map F omega. So omega is defined here, but F omega makes sense in the cover. And all of these lines are mapped isometrically to the real line. That's what comes out of those statements.
And why are you setting as the norm of gamma? Are you assuming that gamma is norm 1?
So right, I wrote this because I started with gamma having norm 1. I was, I just used 1 here. But in fact, the general statement is just equal to the norm of gamma. That's maybe a better way. Yeah, I apologize, I think.
Do we get some nice convex sets in this way, starting from some interesting manifold?
I'm glad you asked. Yes. So maybe the thing to do is actually to give the examples. But let me do that. So,
Is it a lamination or a measurement?
it's a lamination. It's actually important. It's a lamination, and it may not be. It may not have a measure of full support. So it might have isolated leaves that don't carry a positive measure. And actually, understanding what happens on those is in what we are trying to do, which I'll talk about next time. Those extra isolated leaves with no measure are a significant hurdle to understand what goes on. So we spent quite a while thinking about them. And maybe if I get the examples that I want to get to, then you'll see some examples of what happens. Okay? So before I give examples, let me generalize a tiny bit. So this whole story, well, it applies to the homology of the manifold, but I told the story as a story about this abelian cover of a manifold, and I want to think the manifold's compact, and the abelian cover is this cover on which the homology acts. But I really want to think about all abelian covers, not just the ones corresponding to the homology. So let's consider. So now let's consider a cover. Give it a slightly different name. Where M is compact. M is now. Let's make sure I say M is compact. And I'll say hyperbolic because I'm going to forget to say it otherwise. Such that the det group is some group which is isomorphic to z to the d for some d. So an abelian torsion free abelian group. And I want to remark that to connect it to this, it's not so hard to see that this has to be a quotient of the homology group. So, but anyway, there's a bunch of possibilities for this, and that's what I want to think about. And I want to say that this definition, right, the second definition of the stable norm applies just as well. And it gives us a norm on, maybe I'll call it gamma with a little r in the corner. So this is just r to the d, the natural r to the d. You get by tensor just with r. Okay. So it's the same thing. I see in this cover what the distances are, and I take a kind of rescaling limit of larger and larger multiples, and the result is a norm in r to the d. Okay. So well, what about all this? So this seems to lean a little bit hard on there being homology classes involved. So let me just point out a little bit as a kind of side point that when this happens, gamma is in fact always equal to some homology quotient, so some subspace Q in H1. That's just covering theory. And so the dual of gamma, which is Ham of gamma into R, is just everything which is 0 on Q, right? It's all elements gamma in H upper 1 and R that vanishes on Q, right? So the point of that is to say that I can still do all of this, and everything still works. I can still represent any hyperplane by an element of dual space to gamma, and that will be represented by some one form, because it is in fact identified with the subspace of H1, of H upper 1. Okay, so the same discussion happens, and I always have these one forms that I can look for, and in fact the theorem is still true. So this works in the same generality. And so I want to give you some examples where we can actually see what's going on. Okay? All right, let's try that. So example 1. M is going to be a surface of genus 2. So I'm going to draw it like this. And it's a hyperbolic surface. I need to choose, actually, let me just, what's the topological thing I'm going to do? I'm going to build a Z2 cover. I'm going to let gamma be Z2. So the homology is 4-dimensional, but I'm going to make a 2-dimensional cover, okay? So the cover will be this. If I cut the surface along 2 curves, maybe I should draw them in color. Okay, so here's a way to make a cover. I cut along these, make many copies and glue them together, and then I'll have a cover. And here's what I want to do specifically. When I do this, if I make enough copies to glue a series of these together, I will get this picture. So here's part of the picture. Maybe I need one more color. So let's draw this dividing group with yellow. So there's sort of a picture that looks like this. So I feel like I'm giving a course in topology. Okay, so if I cut off the top, here's a Z cover of the bottom. Right? Just take this thing and take the cover that's kind of dual to this curve. So the curve lifts homeomorphically, and then I have this thing. Okay, and then I also want to do the same thing with the top. And the way it will look is this. So in other words, crossing this will correspond to one of the Z's in the gamma, and crossing this will be the other Z. And so if I do that, what's going to happen? So let's add one of these here. So this is a 3-dimensional picture here. So this is actually going in an orthogonal direction. I'll draw one more picture of this to make it a little clearer what's going on. Oops. Yeah, so this connects to here, but this does not connect to here. It connects to another copy of this line. There's another line like this. So you can start to build this picture up yourself. You get this line, and then you draw one of these. You get another line. You get one of these things sitting over each pair like this, and then you keep going in both directions. And one more way to draw this.
So this becomes so big because it's a covering. This manifests the covering?
This is the description of a covering, of a Z2 covering of M.
Okay.
Yeah? I'm going to draw it one more way, which makes it a little easier, I think, to say what's going on. So here it is. It's like a building with a roof and a floor. The roof looks like a bunch of tubes like this. Okay, these are tubes where the blue things live. And then below it, we're looking from above. Okay, below it, there's a family of tubes that go like this. And then that's where the red curves live. Is that okay? And then it keeps going this way and that way, so there's a kind of grid. This picture has a Z2 symmetry, and then maybe the last thing to draw is little elevators here. So these dotted circles are in between the tubes on the top and the tubes on the bottom, and they correspond to these vertical tubes that go from the top floor to the bottom floor. Okay, so there are these elevators sitting here. Everybody okay with that? Okay. So that's a Z2 cover. Okay? Okay, and now I want to do one more, let's see, it's helpful, if I try to do this more explicitly, it'll be helpful to say that to be able to control the geometry of what happens, I want two kind of extra features of the geometry. One is that I want this to be very short, and the other is I want these extra curves I drew to be very symmetric in the sense that each one of them has an orthogonal geodesic to it, like this. Okay, which means when I take this, so there are such hyperbolic structures, and then this orthogonal circle lifts up here to a line that's orthogonal to each of the red circles like that, and there's a similar one on top. Okay, and then the fact that I chose the yellow curve to be very short means that the elevator is very long. So I can't, that kind of separates the top floor and the bottom floor, and you can't cheat by going up and down the elevator in a sort of tricky way. Anyway, what's the punchline of this example? Suppose you wanted to get from one place to another in this grid. So if you started here, pick a base point somewhere, and you wanted to get, somewhere here, remember that, right? So I wanted to get to here. So here's one way to do it. I could go horizontal. I guess I'm starting at the top in this picture. So I could go up along the top, take the elevator, and then go along the bottom, and then take the elevator one last time, right? Now you might say, well, what about some other path? What if I tried to go along the grid with some other more complicated path? If I did a more complicated path that goes horizontal and vertical a bunch of times, I would have to pay every time I change directions by taking the elevator. And so that won't be the shortest path. And especially if I make the elevator very tall, then I can be pretty clear about what the trade-offs are. So as this thing gets bigger and bigger and bigger, I find that the distance, right? So the distance looks like the L1 distance in the plane, right? The distance from here to here, and if I take a very, very large pair of points and rescale the way the definition works, then the geodesic will kind of go over and up or the other way, right? So the limit is the unit ball looks like this. Okay, so this is the unit ball, and this direction corresponds to moving through the red loops, and this direction corresponds to moving through the blue loops. So I have a polygonal unit ball. Okay? Right.
Right, so it looks like this, but it's higher dimension, so it's a cross polygon, it's a hyper-octane.
No, in this case, it really is this dimension, because I took a Z2 cover. So this is an R2. That was one of the reasons for taking a Z2 cover.
So it's a square or something like that?
It's a square. The actual, the width and height of it depend on the geodesic lengths of these white circles, that they basically measure those lengths. So it's so it's not a square, but a rhombus. Okay? Okay, and it's not, okay, and that's, I think in order to fit things in, I won't prove this claim, which is that when I choose, well, maybe it's this. It's, if I take this point, then there are many supporting hyperplanes, and there are many supporting hyperplanes here. But I can in particular choose, if I choose the supporting hyperplane that looks like this, I will end up with a function, the height function, the function that realizes the Lipschitz constant of 1 will be a function which is which takes whose stretch lamination is the pair of white loops that I drew. Okay, so that's kind of the example. What happens in this theorem is that I get this lamination built out of two white loops, which correspond up here to the lines that travel across the bottom and the lines that travel across the top, and those are the maximal stretch lines for the optimal function for this supporting plane. Okay, that's yeah.
If you take a standard Z2 cover, like just in the plane without the upper floor and the lower floor, will the unit ball be completely in the limit?
That is example 2. So let's do that. Well, there are many examples we can do, but I'll example that's partly what you said is example 2. Example 2, I'm going to take the same manifold as before. Okay, but this time I will take a different cover. The cover here will be, so I'm going to cut it along this piece. So the bottom piece is a torus, and this is the homology cover of the torus is a Z2 cover. Right? So if I take the homology cover, so let's call this the bottom surface T1, and this is T2 maybe. So if I look at the homology of T1, Z, that's also a Z2, just this part. And if I take the universal abelian cover of that, I will get a plane with a bunch of holes, which correspond to this hole. So I'll draw it in perspective for a second. So here's the plane. We're looking from above at the plane. And in this plane, there's a bunch of holes. And I guess each one actually looks like this, right? It's an elevator, right? It's a piece of an elevator. It's always hard to know how many parts of an infinite picture one should draw. Anyway, so there's a kind of grid like this. Each one has a little tube associated to it. And the thing I'm not drawing is precisely is the actual metric that this thing has. It's whatever the lift is of the hyperbolic metric, so it's not Euclidean metric. Okay, but it is possible to think about this. And then what about the rest of the cover? So what happens on the other side of the yellow circles? I'm just going to put T2 unchanged. So I'm going to choose. Okay. I want to say this is one of the advantages of being a topologist over a group theorist. Is I can just draw the cover. I don't have to like write down the group. You know, and then other people can figure out the group.
Draw groups.
What? I could draw a group. That's true. Yeah, it's not supposed to be a contest yet. But
It's not a context.
it's not. But ChatGPT can't draw this picture. I think that's my one advantage left to me. Like, yeah. Sorry, I think we have a year or two. Okay. All right. So here's a cover. Right. It's clear that this is a cover. It's a Z2 cover. I want to claim. Okay. Let me answer your question directly and see if I can convince you.
ChatGPT understand these pictures when they come with.
You mean if I drew this and fed it to?
You know, you drew it. You make an argument based on it, and
I
just
think-
convince other topologists. But
I think it can't yet work, right? I don't think it yet. But I haven't really tried very hard because I'm not sure I want to know the answer. Okay, so what? So you asked, I think, whether we just get the Euclidean an ellipse, right? The Euclidean. The answer is no. So here's a sketch of what we get. We get, of course, some kind of convex body. It has a countable set of points which are associated to the rational numbers in the way I'll try to explain. The countable dense set of points where the body has corners. So they kind of look like that. Not a very good picture. So, sorry, what I'm drawing here is a pair of supporting planes.
so if a countable extreme number of extreme points.
There's a countable number of extreme, there's a circle of extreme points, but there's a countable number of points where there's an angle, where there's a non-unique supporting plane. And then there's all the rest have unique supporting planes.
But they are not, the rest are actually straight lines, or they are also extreme points?
They're also extreme points. Everywhere, yeah. In this example, there are all the facets are single points. There's no flat facets in this example. But yeah, that's right.
And
The dual ball, the dual ball in the cohomology has a flat facet associated to each such corner. That's just
but
yeah. Can I convince you that this is roughly the picture? I think we have enough time for. I have till 3, right?
Yeah.
yeah, it's not. The picture is not precise. The picture itself is not what you described verbally. So
This picture or that picture?
yeah, that picture.
So
So you said there are all the points are extreme points, there are no flat.
there are no flat, right, there are no flat intervals in the boundary.
So part of them are there's a tangent. Part of them are like circular, or I mean, how
They have unique supporting planes, so there's
they're unique, but how do they look geometrically? I mean, they're like arcs of a circle, or
no.
No, because-
There's a dense countable set. You should think of this as, in a minute I'll explain why. You should think of these as the rational slopes.
Yeah, okay.
Okay, so for the rational directions,
And so every rational there is a corner.
there's a little corner, right? Okay,
It's a nice corner.
what?
It's a nice creature.
I think it's a nice feature. I like
Yeah,
it.
it even, yeah.
Yeah, I think so.
Yeah.
And I think part of this picture was worked out a long time ago by McShane and Riven, but they never really published the proof. I think they published like a 3-page paper saying the proof was forthcoming. But anyway, this description, as you'll see, is part of a very general understanding of what happens. So I think it's a good example. Okay, so let me try to convince you that yeah.
Does this mean that in this case I no longer have a function that can satisfy, being the same side, being the same norm?
Oh no, the same. Yeah, what happens for? Oh wait, sorry. So what happens? You mean because of the corners?
Yeah, because I don't have any line that intersects like I have here.
What will happen is for each. So there's a family of supporting planes. Each member of the family will have a one Lipschitz representative. And the stretch loci of these the laminations will mostly be the same, but they will vary. I mean, the extreme ones will have slightly different laminations. Anyway, the laminations vary a little bit as you rotate this around, but every hyperplane has a Lipschitz representative. Okay, so let me try and give a feeling for where this is coming from. So let me go back to the Euclidean torus for a second. Here's a torus, just the unit square, except I want to delete the corners. Okay, so identified this way. This is the same as the interior of that of T1. Right? Is this planar torus minus the vertices? And then if I pick an element R in the real numbers, or infinity actually, I can look at, this produces a foliation by lines of slope R. So it looks like this. I'm really happy with that. So the torus is foliated by lines of slope R. And then I can turn this into a hyperbolic picture. And now I'm going to just wave my hands, but let me tell you what the hyperbolic version of this looks like. So, and let me draw the picture in this abelian cover of T1. So the abelian cover of this flat torus is just the Euclidean plane minus the integer points, and in that picture, okay, I have all these lines. And for the moment, let's do the irrational case. So let's assume that if R is irrational, then no line closes up to a loop, and we have this. These all, uncountably many different lines in this picture. Everybody okay with this? And then, what does the hyperbolic manifold look like? Well, the metric changes from Euclidean to hyperbolic, but more interestingly, the punctures become, in this example, they become little geodesic circles. So now I have a hyperbolic surface with a bunch of geodesic circles like this, which is the tops of the elevators, and then inside here is some kind of a negatively curved metric. And then every one of these lines has a unique geodesic representative in this picture. So maybe this line will be maybe goes like that. And as I vary, if I take two different ones, they might be if they're very close together, then they kind of travel through the same parts of the picture until eventually they travel on opposite sides. Maybe I'll make it happen here. Maybe eventually they separate, right? And that happens like this, right? I take two lines like this, and I follow them along until at some point, let me draw it kind of in the abstract, at some point, even very close together lines will come through on opposite sides of a puncture, and then they will look like this, and then they will continue somehow in the picture. So this object is a kind of it's a slightly complicated object called it's still a geodesic lamination. And maybe I should say one more thing to be more careful. The lines that pass through a point, so here's a vertex. The line that passes through this vertex really breaks up into two separate geodesics, which maybe are somewhere, maybe here somewhere. There's a kind of a line like this and a line like that, which stop at the same geodesic boundary component. And as I approach that line from one side and from the other, the limit of all the other lines that approach this is a line that looks like this. There's an extra kind of boundary geodesic here, which is asymptotic to this one on one side and on the other side, and there's one over here. So there's a kind of picture like this. So what's happening is I have a geodesic lamination with an uncountable number of leaves. Okay, and then they opened up to produce a complementary region. I'm going to erase these rays, just leave this complementary region. I have this complementary open region between two limiting. I guess you could think of this: the one that goes into a vertex produces two. You can sort of realize that on one side or the other, you get two parallel things with some stuff between them. So in the if I draw this picture in the quotient torus, I've got this geodesic lamination. It may be kind of complicated, but in its complement, there is this region which looks like this thing. It's what's called a punctured bibound. It has two vertices in infinity and then one boundary component like that. Okay, so what was the point of all this? I guess I want to show that this object, which it's an object on the surface, will be the stretch locus of a one Lipschitz map in this configuration. Okay, and here's how we'll do that. I'm going to just make a bunch of claims about hyperbolic geometry. So look at one of these regions that I just talked about. So remember, this is a hyperbolic surface. This thing kind of comes out. It's quite perhaps long. But this thing has a nice structure which looks the following. Everywhere I look inside this region, I can ask where's the nearest point on the boundary. And I would get there by drawing an orthogonal arc like that. And sometimes I'm on this, sometimes the nearest point is on one side and sometimes on the other. And in fact, if I draw the whole picture, I get there's kind of a region in the middle which is equally close to both sides. And so if I draw this kind of carefully, I'll get a picture that sort of looks like this. There's a kind of, these are orthogonal like this. There's actually slightly, so yeah, I'm running out of time to really draw this carefully, but there's some kind of a foliation of this complement so that every point is close to one side or the other. And then if I look at, I can do this in this region, and also in the plane, I can do it to all the copies of this region, so that the fuller picture looks like this. There's this region, but there's lots of other copies of it which come very close, maybe like this, and so on. And in each one of them, I do the same thing. So I've built a kind of foliation of the whole surface, except which looks like this way around the boundaries. And then I can. This gives me a function. The function is this now. I take any point. Well, you have to be a little careful. I want to define the one form. So the one form omega, which I want to define, is the one which measures along the leaves of this lamination is just arc length in a fixed direction. And everywhere else, let's say over here, the way I get a one form is by projecting along this foliation to the boundary and just pulling back that same one form. So I have now a one form which is defined in the whole surface, which is just a pullback of arc length along this geodesic. And that one form has length 1, because and this is a hyperbolic feature again. If you look in hyperbolic space and you look at the orthogonal projection to the geodesic, this orthogonal projection is always retracting, it's always shrinking, and that means that take a vector out here and you push it to the boundary and take its length, it will be smaller. So that gives you this inequality. So this omega is less than or equal to 1, and f omega will then be 1 Lipschitz. You might complain that the way I drew this doesn't look like it's continuous here. And in fact, it is not continuous. But it still defines a cochain. And so it still works. So anyway. So this gives me a function which has the property that it exactly takes this lamination of irrational slope and gives it its maximal stretch. And so that means that, well, so to be precise, this lamination will become the stretch lamination of this Lipschitz function, and that will account exactly for one of the points on my boundary. So there's more to be said here. This is not just a lamination, but a measured lamination. And so this lamination actually defines a homology class. And that homology class lives somewhere in the boundary of the unit ball, and I have explicitly given the hyperplane that this one form defines. Okay? Let's see, I've cheated you a little because I only defined this on this surface and I didn't quite define it on the top surfaces that came along for free. Right? The little top bulbs. But it's not hard to see that I can essentially, the function I produced, I can, if there's enough room in this elevator, I can just kind of extend it so that it's 0 over here. So without changing the Lipschitz property. So you have to do a little adjustment. But this produces a function that is a supporting hyperplane for this. I guess I didn't prove. This doesn't quite prove that there isn't another one. That maybe there's another one. So I'm not going to prove that.
Another what? Another omega?
Sorry, this doesn't prove, what I said was this kind of is a proof that there's a point on the boundary for which this gives a supporting plane. I didn't prove it's the unique supporting plane. Okay. So, what it is.
Some of this process takes defoliation and produces a lamination.
Yeah, that's right. So because I drew it this way first and then I turned it to a lamination. That was a trick to be able to say what this lamination is without working too hard. In a general surface, you don't have the torus model. And in a general surface, not every lamination works. So there's a kind of, maybe I'll say that there's a, so there's a theorem of Calderon and Farr. Let me say kind of informally, for every measured lamination, mu satisfying some condition, satisfying a homological positivity condition, which I won't write down. Apologize. There exists a hyperbolic metric for which U is a stretch locus for one of these things. So in the case of the punctured torus, every lamination actually arises in this way. Every measured lamination arises in this way. I did it for the irrational ones, but you can do it for the rational ones also. In a general surface, not every lamination does. You actually have some conditions. But
You just said it's a lamination, not a measured lamination. Now it is a measured lamination.
right.
Where does the measure appear?
The measure appears. It avoids. So the right condition is chain recurrence. So for every chain recurrent geodesic lamination, there's a certain positivity. It has to intersect some curve in a positive way.
But you don't see the measure in the
You don't see the measure, right? Well, yes and no. So right. The construction doesn't use the measure on the lamination. It does use a certain recurrence property. When you're done and it's the stretch locus for something, you can look at the measures supported on the lamination, and those measures give you homology classes that live in the facet that you have produced. So if you found a function you found this kind of supporting plane. The supporting plane meets the unit ball in the facet, and the points in the facet correspond to measures on the lamination. So the measure plays a role. I said homology, but we are doing this. This is ending up in the. There's another story here, which is which cover am I taking? I didn't quite talk about which cover I'm taking, but
Is there a intuitive reason why the stretching? Why did you get lamination for this function? Where the
yeah, sure. Yeah, I couldn't meant to draw this picture. So,
in general, not
suppose you had a one Lipschitz map, which actually realized the Lipschitz constant somewhere. For example, if you have a Lipschitz, suppose you have a Lipschitz, let's say one Lipschitz map from some manifold to R, and suppose that there was a line where suppose there was a line or a segment even where F is in isometry. Okay, this is like a stretch locus, right? So I claim once you have one, you can't have crossing with another one. Because, look at this picture. Suppose I had a function defined which is an isometry on this line and an isometry on this line. Then if you take 2 points, the same distance, let's orient it. 2 points, the same sign distance from the intersection point, they have the same value of F, but they are just, I want to do it the wrong way? Sorry, the other way. This way. Sorry. These 2 points, the difference of their F values is the length of this path, but their distance is smaller, so it can't be one Lipschitz. Right? So that's maybe the basic reason why you can't have self-intersections with the stretch locus. Which I meant to say maybe a while ago. Yeah. Okay, I think I'm out of time, right? So I will stop.
Thank you. Questions?
Do you get some nice convex sets or pairs of convex sets in higher dimension?
So we know very little about the picture in higher dimensions.
But you just need to mod up not by zero, but by something.
Do you mean higher dimensional manifolds or higher dimensional covers?
Higher dimensional covers is what I meant, but
What do you mean?
So you could take z to the d for d bigger than
Z to the D.
for large d.
Do get some nice convex sets there?
So one I don't know what question you mean. You could ask, given any convex set, can I realize it as the convex set? I don't think I know the answer to that.
But here you got fairly exotic types.
That's right. So for example, they're certainly not going to always be polyhedron, but they can be sometimes polyhedron.
Here it's not
Okay.
polyhedron.
That's right.
Is there some dimension bound on the largest dimension of the facet?
I think the largest dimension of the facet is half, because there's kind of a Lagrangian property.
Why do you have the Lagrangian?
So when you, this is kind of just a feature of the measured lamination space, that if you have a lamination that supports many measures, the biggest dimension of the set of measures it can support is half the dimension, because intersection number acts like an intersection. Intersection number is like a symplectic form, and all of the measures on a single lamination line in Lagrangian.
So this is a symplectic structure?
Yeah, this is called Thurston symplectic structure on the measured lamination space, and it just comes from correctly viewing the intersection.
So it cannot be polyhedron if the maximum dimension of the face is only half the dimension.
Except to this dimension, I guess so. Yeah,
Right.
maybe in dimension 3. No, not in dimension 3. That's a good point. I haven't thought about that question. Yeah. But generally, yeah. So, yeah, there are not, I think, a lot of examples worked out in detail. Maybe just these sort of simple things are the only ones. Certainly, the only ones we've worked out look like this. Yeah, I think it's an interesting question. What convex bodies do you get? This is like somebody you asked before about whether it's related to Thurston's norm, and this is kind of a qualitative difference. Thurston's norm on second homology is always polyhedral.
Do you have any theory for second homology? It's not,
Like, that's like this, you mean?
it's not, yeah, the none that talks to me.
But this volume.
Yeah, because you define it to start and define
I
it.
I started defining it right for any dimension. That was just for completeness. I don't think I know much about that. I mean, presumably, so I think again, kind of the things I realized that any given class have to be minimal surfaces in dimension 2. Yeah, I don't actually know anything about this. Interesting question. I think some of these tools that are used in describing this are not quite as flexible in higher dimensions. Like the relation here between this norm and distance on a manifold, I think, is special to one dimension. Yeah.
So I thought we were supposed to see at the end there were like 2 supporting planes for rational points and 1.
I never got to the rational case. So, right, for the irrational case, I didn't actually explain why it's just why there isn't one. I think it's essentially, you can probably do it by continuity, but I didn't explain the rational case to show why there is an actual angle. Let me draw you one picture, okay, for the rational case. So, oh, the white picture. Okay, let me make it quick. The picture is this. So, the corresponding thing to what I did in the rational case, it's actually going to look a little bit similar, is instead of this thing, which encases exactly one boundary component and then squeezes together, you end up encasing a sequence, because it's a rational. In the rational case, you have a kind of periodicity. So there's a picture that actually sort of looks like this. That. Exactly where it is. There's sort of a picture like this, where this is supposed to be the leaves of the lamination. It's just a countable collection of leaves. Okay? And now I can complete this to a slightly larger lamination in 2 different ways. One is, I can draw, let me draw one leaf like this. It's asymptotic in backward time to this, and then it climbs up like this, and then back like that. And then all of its translates look like this. Okay, so you have to sort of believe me that I can make this whole picture geodesic inside the surface. That's not, I think it's pretty obvious. Except straightening things to be geodesics always works in hyperbolic. So anyway, now I have this picture. I've completed the rational thing to this picture, and now here I have another copy of the same sort of thing I had here, and I can do the same story. I can now build the same kind of projection from each one to its boundaries, and I can build the one form in the same way, and it gives kind of a stretch factor of 1 on the horizontal lines and also on the yellow lines. Okay? That gives me one supporting plane that sees these curves. And then I can just do the same thing. I can now erase the yellow lines and draw lines that do this. Okay, and I can build another one. Now, right now I can build a new map, which has the stretch direction. The stretch amount is 1 along the red arcs instead of the blue for the yellow ones. And what this produces is a different cohomology class. And so now in the, I'll sort of have a picture. Each. Yeah. So now there's 2 hyperplanes, the red one and the yellow. So somehow these 2 pictures, yellow and red, produce 2 different one forms, which give me the 2 tones like this. And so somehow the fact that I can rotate, kind of 2 different one forms has to do with the fact that in the complement of my lamination that I drew, the horizontal one, there's still stuff in the surface. There's room to draw more leaves. And so I can draw them different ways, and I get this thing. And whereas in the irrational case, the lamination itself already ate up all the space. There's nothing more that I could change inside here to produce a different map. That's the rough.
What's the angle?
I don't know. I don't know. So it depends on the length of the curve. Maybe the shortest. So
There's not like a closed formula, or anything, like a rational number or something?
I don't know close formula, but I never know close formula, so it doesn't mean much. My estimate is that it should be exponentially small in the length of these closed curves. That's my guess.
Which was it?
So this horizontal line had to do, I drew it horizontally, but it came from some rational slope on the torus. So for each slope, I get a closed geodesic that has a length. And I think that e to the minus that length is a good estimate for this angle, but I couldn't swear to it.